Good afternoon, everybody.
Good afternoon, sir.
Good afternoon, sir.
So today we are going to start the new chapter. We will start chapter number 3. Okay, so chapter number 3. However, actually we also go parallel. So we will take up a problem which is in chapter number 3. Then we take some steps to solve it, which are in chapter 3, 4, 5. So the way I'm going to teach, I will take 3, 4, 5 in parallel. Not that we finish chapter 3 first and then 4 and then 5. Is because how it is organized. The book is organized is chapter 3 is talking about all the problems. Chapter 4 talking about how to approximate the solutions, and chapter 5 is actual solution. But what we will do is we take up a problem and we go till the end. Okay, so that way you will follow it better, and hence we will teach that way. Okay, now what happens is chapter 2 where you studied the direct method. Now we are delving into equations now. Okay, so structural equation or 1D bar or 1D elasticity problem. 1D elasticity problem. Okay. Now you have already studied, and you know that is examples are these. You know already if you are in the force here, area is AE, so then how immediately you know sigma equal to F over A, all the kind you know already, right? And we have formulated as a direct approach, and a strain is given by sigma over E, so F over EA. So all those you know automatically, and if it is a U here, and accordingly you know that K equal to EA over L, and hence U will be F over K, and that you get FL over EA. Yeah, and where U is given here, this by the other end is fixed, and this is like this. If there are a series of bars, and then so if there is a series of bars, and in that case what you do, you have K1 and K2, and based on that you solve the problem. So this you know. Now what we don't know so far is what happens if the equation is given. Remember that finite element analysis came from mathematicians, so this can be applied to different problems as long as it satisfies a certain conditions, so I mean that's what we will look at. We will now look at from mathematics point of view. So let's first study what is 1D elasticity problem. Yeah, okay. Now problem could be something like this. So you have a bar which may be fixed at one end. The area of cross section may be varying. There may be some body forces, call it Bx, which is a function of x. Young's modulus can also be a function of x. Area of cross section can also be a function of x. The x is in this direction, and accordingly even u will automatically be a function of x. This is the displacement. So we are making a general purpose problem, complicated problem, where Young's modulus is changing with x, area of cross section is changing with x, and there is a body force. Body force is something like, one example could be if there is a bar which is hanging from the ceiling, and because of its own weight, you will see the forces in that, right? And what kind of forces will be something like C. It will be something like this. Means at the end, if you see there will not be any tension, but here there will be a tension. Yeah, here will be the highest tension because everything below this point is hanging from here, so maximum force will be here and minimum force will be here. So that means this is the what Bx is. Yeah, Bx is here, it will be 0 and it is linearly changing up. So this is just one example. Yeah, and similarly it could be in different problems. If let us say this in magnetic field, if you put a bar, then it will have a similar kind of problem and all, you know. So accordingly, body force can exist. So this is the problem. Now we have to find out, first of all, what is the equation? What is the equation that it is following? Equation wise, you can, what we will do, we will take a slice. Yeah, so we'll just cut, we take a small slice from here. Yeah, and a small slice will have something like this. It will have area here, it will be AX. Here it will be AX plus DA over, right, D over DX. So area here will be this and this. Similarly, you can have Young's modulus as well. Here it will be EX, and at this section, this will be EX plus DEX over DX multiplied by DX, because this is DX, right? And similarly, we can have sigma. So which all things we have? We have a sigma here, right? This is the force, which is sigma. So sigma x, and here it could be sigma x plus d sigma over dx times dx, and so on. Yeah, this is how it will be. Okay, now given this, always we have to find out the equilibrium. Equilibrium is summation of all the forces in x direction has to equal to 0. Have we pointed out everything? One thing we missed is this. It also have body force Bx. The Bx is in Newton per meter kind of unit. This is distributed force. So we also have Bx. So we write here Bx. Accordingly, we find out, depending on what the volume is, we have to find out what's the actual total force. Now, total force has to be equal to 0. Hence, this is sigma x, right? Force here will be sigma x, which is a force per unit area multiplied by area AX. So at this negative direction, so we will have minus. Yeah, so we can write like this, minus sigma x multiplied by AX is the force here. Similarly, in this direction, we have this multiplied by area. So plus, we have sigma plus d sigma over dx multiplied by a plus d a over dx. So we got that this multiplied by this minus this multiplied by this. Okay, and then we have this as well. The direction is in positive x direction. So we write that also. So we will write plus sigma. Okay, so let's write here. We say plus here, plus we have bx multiplied by length. And what is the length? Length is dx. Yes, so multiplied by dx is equal to, total has to be equal to 0 because this is a static problem. So this multiplied by this means total force in this direction minus this multiplied by this, which is total force in negative x direction due to the section forces. And then you have this body force. So this multiplied by length dx. So this equal to 0. So this is what our equation is. Okay, so this is the equation we got from here to here. and we can expand it. So we have, if you expand it, what do you get? So we get sigma times A plus, then we have sigma times A plus sigma dA over dx plus d sigma over dx A plus d sigma over dx dA over dx. So I have expanded this term I have expanded. Yeah, so this multiplied by this multiplied by this, then this multiplied by this, then this multiplied by this. Okay, I think we forgot to multiply by dA dx. So here we go dx, and here we will have 2 dx, right? So dx multiplied by dx, like this. Okay, so not this. Okay, so sigma A, and here it should be minus, and this is plus. So minus sigma A plus sigma expanded version sigma A, and this times dx, this dx here also, and then dx and dx 2, because there will be dx multiplied here, the dx multiplied here. Okay, plus we have dx times dx is equal to 0. Now see here, this and this will cancel out, right? Here minus, here plus, so this will cancel out. So we have sigma dA over dx times dx plus, now this d sigma over dx, right? Then a dx plus, now here you see we have dx times dx, second order, basically very small. Dx is to begin with a small, so dx squared will be very small, that can be neglected, so we will not write this. Okay, so we will make this equal to 0. Then we have this and this cancel out, so we did not write that. Okay, plus now we have this dx, so dx times dx equal to 0, or what do we get? So we have dx here, dx, we can get rid of that, so we get or sigma dA over dx plus d sigma over dx A plus bx equal to 0, or we can combine them together, and this will be simply d over dx sigma A plus bx equal to 0. So this is one equation we got. Yeah. So this is a 1D elasticity problem. Any question, guys?
Excuse me, sir. Yes, sir.
Yeah.
I have some doubt. Actually, I'm Shubhana. Sir, why you make it 0, sir? D sigma by dx and dA by dx into dx. Could you please explain again?
Okay. Here the whole term is 0, not this is 0, not this is 0. Dx times dx is there, right?
Yes, sir.
So last term, if you see what happens, last term is d sigma over dx multiplied by dx, and this will be multiplied to dA over dx multiplied by dx. So d sigma over dx may not be small, but we have dx here and dx here. So if you multiply both, that becomes equal to negligible. Right?
Yes, sir. Now it's clear, sir.
You have delta square, right? So we have delta square order. So that is negligible, and hence we got it.
Yes, sir. Thank you, sir.
Okay. Okay, now we got this equation. Only thing is we have to write that equation in terms of u, because unless you write sigma in terms of u, we will not able to solve it, because
Sir,
our variable, yeah.
Yeah, shouldn't we use partial derivative, sir?
Partial derivative, no, because this is 1D problem. Only you have only x only variable. There is no other variable. Yeah.
So sigma is only varying with x only then.
Yeah. Yeah. Yes. Is it 1D problem? No. There is a partial derivative, but we will do later on after mid sem. Okay. We have long way to go. Okay. So we have to convert this sigma into some kind of some function of displacement, and how do we do that? What we got so far is based on the Newton's law, right? We make a total force equal to 0 because it is a static equilibrium. Now we have to apply Hooke's law or material property. So Hooke's law, and Hooke's law says what? Sigma proportional to epsilon, or sigma equal to E epsilon, or sigma x equal to Ex and E strain. Yeah. Okay. The same thing we can write there. Instead of sigma, we can write these things. But again, we don't know what a strain is. What is this? This strain is nothing but, this comes from Hooke's law. Then what we know is as a kinematics or displacement strain relationship, main strain relation. Yeah. And this says strain is equal to nothing but du over dx. So we have three equations. One equation is coming from the force equilibrium. You say force equilibrium or equilibrium equation comes from physics. Now, second is what is we call it material property, Hooke's law, or is also called constitutive relation. And third, what is you call it kinematics equation and or displacement strain relationship. Okay, so you can call it one. You can call this one as number 2, and this you have number 3. So from 1, 2, and 3, if you combine them together, then what do you get? You get d over dx, and then you have sigma times a, right? You have sigma times a. So we write sigma in terms of Young's modulus and strain. So we write Ex times a strain, but a strain is given by this du over dx. So we can straight away write du over dx. Right? So we are replacing this with this. Area is also there. Yeah. Multiplied by yes. Yeah. You are right. So yeah, multiplied by ax. Correct. Thanks. Plus bx equal to 0. Yeah, and you can write d over dx ex multiplied by ax du over dx plus bx equal to 0. So this is what you know it as 1D elasticity problem. Now you have this differential equation. Now you can solve it. Only thing is you need more thing, and what you call it boundary conditions. So depending on the problem, the boundary condition will be different. It's possible that you can have boundary condition of different types. One, what we call is essential boundary condition. essential boundary condition. Okay, and in this you give, for example, if you fix the left end of the bar, for example, yeah. So this u at x equal to 0 equal to 0, if you write like that, essential boundary condition is applies to the variable itself. So applies to u itself. So if you are saying u at x equal to 0, then this is what call it essential boundary condition. In this case, you have done like this. The other end could be any, you can apply force, for example, right? The other end here, if you get F naught. Yeah, and if the other end is force, then we have to write accordingly. So force at, if you write force at x equal to L is equal to F naught, we cannot write like that because mathematics would not understand what the force is. We have to give in terms of u. And how do you do it? You do in terms of force is nothing but sigma times A. So you are telling that force as x equal to L is equal to sigma times A at x equal to L is F naught. And sigma, you know that sigma is Ex, right? Ex times Ax times du over dx at x equal to L is equal to F naught. So this is what you will write if you are giving force value. Yeah. So this multiplied by this is a strain, this is Young's modulus times a strain, it gives you the stress multiplied by area gives you the force at x equal to F naught, you are going to write here. But what you see here, you are applying a boundary condition on the derivative of u. Yeah, and this is just known as natural boundary condition. Meaning that boundary condition on derivative of the variable or du over dx. Yeah. So you can give two types of boundary condition. In general, if you are not writing explicitly, that really means this value equal to 0. Automatically, this equal to 0 is automatically applied everywhere. If you have not applied a force, that really means force value is 0, right? As simple as that. If there is no force defined, if you have not applied force, means force is 0. And that means natural boundary condition automatically 0. When you solve it, automatically it solves for natural boundary condition equal to 0. Any question, guys, so far?
Sir, I'm Shubhanath. Sir, actually, in that derivation, sir, why don't we apply any kind of point load or point force? Sir? Can you please?
No, point force only I have applied. This is point force only, no?
No, sir. Previous one, sir. For the equation, for the dx equation, sir, we did not apply any kind of point load, point force. We only apply to the boundary force, right, sir?
No, I'm not getting you what you are saying. Which one?
Sir, for the first derivation, sir.
This
Yes,
one
sir.
you are talking
From
about.
this derivation, yes, sir. We didn't apply any kind of point force. Okay, sir. Is it?
No, those are boundary conditions. No, point force will automatically be captured in Bx. We have the body force, no?
Okay, sir. Okay, sir. Okay, sir.
So in our problem, remember that we have, this is the body and these are the boundary. Boundary number 1, boundary number 2. Yeah, there are two boundaries only. And in between, whatever we have is a body force. So body force can be in terms of point force as well. Yeah. You can define body force as a point
Okay.
force. That will be a direct
Okay, sir.
delta
Now it's
function, right? It will be like a direct delta
okay.
function.
Okay, sir. I got it, sir. Thank you.
Okay. Okay. So finally, you can summarize your equation becomes d over dx EA du over dx, right, plus bx equal to 0, where we understand that E can be a function of x, A can be a function of x, where and with boundary condition or subject to, we can have example. You say example, boundary condition is example, boundary condition which can be u x equal to 0 is equal to 0, and it can have EA du over dx, right, at x equal to L equal to F naught. So this gives you a complete definition of the problem, and you are supposed to solve using a finite element analysis. So solve the above using a finite element method. Okay. Okay. Now, this is what you study in chapter 1. Okay. In chapter 2, you go to study the approximate solutions. Yeah. So finite element solution is nothing but a approximate solution. Yeah. Approximate solution. Okay. And what is the meaning of approximate solution? Now, let us say we want to solve this problem. Yeah. And we start, you can assume some value, and based on that, we can solve it. Now, approximate solution, there are different way of solving. One way of solving is what you know is Galerkin methods. And in that, what you do? You do like this. You have this problem, something like this one is equal to 0. You see this problem. What it does is, you assume the approximate solution U is equal to, let us say, here we can say U dash maybe, or let's call it U dash. Okay, U dash doesn't mean this is not a derivative. Use just approximate solution U dash. Exact solution is U, but approximate solution is U equal to U dash is the approximate solution. And in that case, what happens? D over dx EA du over dx okay, sorry, not dx, plus, yeah, plus, and here we have, yeah, is all right, yeah, then bx, okay, and then we have multiplied by some weight w. So here we have u dash, remember, so because this is approximate solution, so we, instead of we put u dash here, because that will be the approximate solution. We have this multiplied by w times dx equal to 0. What we did, we integrated it with what? We have this equation, we multiplied by a weight, so we call it this is a weight, and we have integrated over equal to 0. Now we are saying that u dash is an approximate solution, and this satisfies this condition. Here we will have the, of course, this has to define over the whole domain. So we can write is omega here, or here, sorry, the line here. Okay. Yeah. So this is over the whole domain. So it is from 0 to L defined. So we have integrated over the whole thing. And as long we are saying that the original differential equation, we multiplied by W and integrated over the whole domain. And we are saying that if this condition is satisfied for any W, then we call it U dash as an approximate solution to the original differential equation. What is the difference? What is the between, let us say,
Sir,
yeah.
Sir, this solution will be to the initial boundary condition, essential boundary condition.
Whatever boundary condition we are giving, we have to apply those boundary conditions. Yeah. Boundary condition we have to apply anyway. Yeah, that will be like essential boundary condition you have to apply anyway. Okay, so for the natural boundary condition, we don't know whether it will satisfy or not. But essential boundary condition, we have to. So you can write here U dash satisfies the its essential boundary condition. Yeah, fine. Shubham,
Yes,
okay,
sir.
okay,
Yeah,
okay
yes,
now.
sir. Now it is good.
Okay. So we have to make sure that this satisfies the essential boundary condition. Yeah, but natural boundary condition, we don't know it satisfies or not. That we can check later on. But this is how the setup of the problem is. What is the meaning is, if U, which is the exact solution, let us say if you are plotting it. So if you are plotting it with X, and here you have U, and then the value, what is this value? This value is this. What is you know as receipt. Like phi x is equals to, right? You write like this, phi u. Phi u is equal to d over dx Ea du over dx, right? Plus dx equal to 0. So this is phi u and phi u dash. Phi u dash. So if phi u is like this one, and it has to be 0 everywhere, right? And hence, if you plot, if u is exact solution, then value will be like this, 0 everywhere. It will be 0. But
So this
yeah,
equation that you are writing, phi u
Hmm.
equals to this whole, which we have derived from a particular 1D case. Sir, it's not necessary to be applicable everywhere. We'll have to find our own.
Yes,
Okay.
true. Yeah. It will be a unique solution depending on the boundary condition. Yes. Yeah.
Yes, sir. Yes, sir.
But still, this will hold true everywhere, because this is the basic equation that we got, right? So regardless of what boundary conditions are, this will always be true. And when you exact solution, this will always be 0. And hence, I'm plotting this as a 0. Now, second condition, if you see, like say, if you have the approximate solution that you are going to find as Galerkin method, then what happens? It is telling that you can be not necessarily like this. Yeah. So as long as you have that value like this, it's like, it's possible that, what is this? This one is this. Phi u w, like this, yeah? Dx 0 to L. Sorry, I think I should not write like that. Rather, we should write like this. Phi u dash multiplied by w, right? Or you can also write any w here also, because this is 0 anyway, multiplied by any w will also make it 0. So if it is exact, it will exactly be equal to 0. But if the approximate solution, you are allowing it to be something like this, as long as phi u dash w dx 0 to L equal to 0, you are fine with it. And you see here, this, since it is a wave, it goes up and down, goes up and down. So if you integrate, it will be equal to 0, right? Is it possible? Right? So, but the thing is, your u is different now. Your u is different, hence you get this as different value. So this is what the approximate solution is, meaning that your racid, all call it error. In a way, you are distributing the error. You are minimizing the error. So approximate solution is there, but it has to satisfy some condition that you are telling, right? Any question, guys? Okay, so basically, Galerkin method will have one what is called is a strong form, and a strong form in this case is what? Is d over dx Ea du over dx plus bx equal to 0. This is a strong form, and there is equivalent weak form, and weak form is, you get it by integrating from 0 to L, then you multiply it by w, then you have dx Ea du over dx, right, plus bx dx equal to 0. So this is weak formulation. Why weak formulation? Because this solution of this may be the solution of this. Yeah. Of course, boundary condition we are talking about. So here for any w, okay, so that's important. This has to be any w if this has to be equal to 0. Now what happens is, exact solution will be a solution of that. Exact solution will be a solution of this, as you know that if this equal to 0, this will always be 0, and 0 multiplied by w will be equal to 0, hence it will always satisfy. However, solution of this not necessarily will be a solution of this. Solution of this will not necessarily be a solution of this.
Sir,
Yeah.
for in weak form, we should be using u dash, na?
Yeah, well, so here, not necessarily you have to use u dash. I use just to make you understand, But here, in your mind, you can have that this u is nothing but this is different to you. This is different to you. Yeah.
Okay, sir.
Yeah. Otherwise, u dash will be confusing. That's why you don't use it. In your book also, it will not be written like that. Yeah. Just you understand that once we have applied, this is a function fx, right? You cannot write x. See, in every problem, x will be different. What you meaning that your coordinate system will change, so but you don't write x dash and all, everywhere you write x only. So in a similar way, u is the universal dependent variable we use for displacement and even for temperature and all. So u dash I use just to make you understand that this u dash is approximate solution, this is a different. Once you understand, then we do away with it. So we are back to, we will use u only, otherwise it will be more confusing.
So we can generalize that by a weak form solution, we will get something approximate, and by the strong form solution, we will get an exact solution.
Sure. So you can write, sure. So you can write, so this understood. Here u is the approximate solution, right? Okay, that's what I'm telling also. I'm writing right now, but I'm telling the same thing. And here u will be the exact solution. This is what the meaning, weak form approximate solution. We started approximate. You remember we wrote here approximate solution u dash, and then we wrote like this one. Yeah? So just to relate, basically we are writing like this one, u does satisfy sensible boundary condition and all. Yeah, and then here, just to compare, I'm comparing that approximate solution will be like this, this exact solution will be like this. Yeah. Once we have done that, we are back to remove the u dash, so because we are going to work on it more and more, so but here the solution of this will be approximate solution of this approximate solution to the original approximate solution to the original differential equation. Is fine.
Sir, can I ask something?
Yeah, go ahead.
Sir, from this equation, can we say that the strong form must satisfy the both the boundary condition, and the weak form only satisfying for the essential boundary condition, sir? Can we say that?
Yeah, you can say that. Sure. Yes.
Okay, sir. Another thing I want to ask. Sorry, pardon, sir. Another thing I want to ask that there are several. As far I'm just a little bit asking that rather than Galerkin method, there are several methods for taking the approximate solution, such like weighted residual method. These are the. I'm just asking, sir. Actually,
weighted residual. This is the weighted residual, na? You have W, no? So this is weighted residual only. There are other method, these method that we will
root mean square. Okay. Yeah, okay, okay, sir. Thank you, sir. Thank you, sir. Okay,
other method called Rees method we will follow. We will do later. Okay.
Okay, sir. Thank you, sir. I got it.
Okay. So we have the weak formulation, which so far 0 to L, then W, then D over dx, then dx plus dx equal to 0. Now we are going to expand it. Yeah, expand, and then what will you get? You get 0 to L W d over dx EA du over dx, right? Then dx, dx will not be there here, guys. Dx, we have a dx like this, then plus W dx is equal to 0. So this is 0 to L. Yeah, okay. Done. So we have two parts. One part is this one part is this one. So write 1 plus 2 is equal to 0. We will take at the first one, I equal to 0 to L, then W d over dx, EA du over dx, yeah, and then you can do integration by parts, and then is equal to, we can have W multiplied by EA du over dx. So you have L and 0, and minus, right? Minus, you will have 0 to L, right? And you will have EA du dx, and then you will have dw over dx. So this is by integration by parts, which is like u dv is equal to uv, right? So let us say 0 to L, so you have 0 to L minus v du. So this is what the integration by parts is. Yeah, so we applied that, and is equal to, what do you get here? W EA, so you can have W EA du over dx, x equal to L minus W EA du over dx, x equal to 0, minus, so minus 0 to L EA du dx dw over dx. Yeah, so we got first part like this. So we know that number 1 plus 2 equal to 0 is the whole equation. So we can write further, and what do we get? We get like this. So we have WEA WEA du over dx. So we will write all together. EA du over dx, x equal to L. What is this value? So we will come back to this. Okay, so now WEA du over dx at x equal to 0 minus 0 to L EA du over dx dw over dx, and plus 0 to L w dx, all equal to 0. So this is what the weak function is. Yeah, so the weak formulation. Now these values, if you know by a boundary condition, you can do apply all of this. If you remember that we said that at this is L. So at x equal to L, f equal to f naught at x equal to L. So this really means EA du over dx. So E times du over dx, this is a strain, a stress multiplied by a force at x equal to L is equal to f naught. So if you see here, what do we get? EA du over dx, this is nothing but f naught, right? So we can write that here. If you had the boundary condition, you can write it here. Yeah. Okay, now there are some conditions that impose when we are going to apply the Galerkin method. Okay, so Galerkin method, we choose W. Remember that this is true for all W's. So regardless of what W you choose, for all W, This is true. And you choose W such a way. W is such a way. Such a way. W equal to 0, where U is given or prescribed. Okay. This is how we choose W. Okay. So because that is true for any W, so this is your discretion basically, what kind of W you want to choose. So you can choose a W which vanishes where U is defined. So look at our boundary condition, example boundary condition, and what we did in that, U equal to 0 or Ux equal to 0, U at x equal to 0 equal to 0. So automatically W at x equal to 0 equal to 0 because U is defined here. Second one here, F is defined, or you are saying EA du over dx x equal to L equal to F naught. So here we don't know what the W is, right? Here W will not vanish and W will be x equal to L, whatever value that will be. So if you apply these these conditions over the weak formulation, then what do we get? This is nothing but F naught. So we get W F naught. Then we have minus this. Now W is equal to 0 at x equal to 0. Why? Because U is defined there. So this whole term will be 0. So we will not write, this becomes 0. This example how we are working out. And then you have this term and this term. And then you have plus, minus 0 to L EA du over dx d W over dx plus W bx dx 0 to L is equal to 0. So you see, you have put in this format, or this value you can take the other side. So you get 0 to L EA du over dx dw over dx is equal to W F naught plus 0 L W bx dx. So we have this form. Same equation, we have what we did. We have changed it. I changed it, and how does it look like? See, this is the approximate solution. Original differential equation, if you look at, you had this look like something like this, meaning that you needed to be double differentiable because one derivative you get here, the other you get here. But finally, we have found a solution where double differentiability requirement is gone. We have just single differentiation here, you see. So that really means that we can find some differential, some approximate solution, which actually can be just single differentiable. So meaning that although as per this, you can think that the solution has to be at least quadratic, if looking at it. Yeah. But here, looking at this, it looks like even if you have a linear function, that can also be admitted as a approximate solution. So this is the beauty of this Galerkin method, that you can admit like low order functions also as the solutions. Any question, guys?
Sir, you have mentioned two things here. One is weak form and second is weak formulation. So are those the different
Both same,
things, or
both
are
same.
they same?
Both are the same.
So So previously you have mentioned the weak form. There the differentiable requirement was two order. U has to have a two order equation, something like
No, no,
that.
no. For
But after integration,
the strong formulation, differentiability here is 2, but for the weak formulation, got it?
so isn't
For the
that
strong
that you have
formulation,
mentioned
no?
previous? That is the strong form only.
Yeah, yeah.
There is one equation which governs the condition that is different, and can be integrated with the weighted function. That is a strong form. And after integration,
No,
that
no,
comes
no,
which
no.
is
No, no. You are saying other way around. When you integrate it, it becomes the weak formulation. The original differential equation is called the strong formulation.
so previous was the strong form, right?
Right.
Without integration, when we
Sure.
haven't integrated.
Yes. It's fine?
All right, sir. All right, sir. All.
Okay. Any other question? Okay. So in the next class, we will solve it. Okay. Solve it means we will actually apply the Galerkin method, and we will see how we can find out some approximate solution to a real problem. So based on the method what we have used, we can assume W value, we can assume U value, we can and see whether really it works or not. And if it finds out what kind of solution we get and how to find out the solution. So when you follow the steps, you will automatically know the meaning of that, how approximate solution is different from the exact solution. Yeah. So we will do in the next lecture class. Okay, guys, if there is no further question, see you later. So remember that there may be something which may be not be understanding, but as we go ahead, we are going to repeat more and more, and we will understand more and more. It will be easy to understand. Yeah, okay. Okay, guys.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.